Hi, if we haven't met, I'm Phil. I created the original PureScript compiler, and I continue to work on it. I'm going to give an overview of the PureScript type system specifically. So, just the type system, PureScript, the entirety of PureScript is kind of a big topic to present in like an hour, I suppose. So I'm just going to focus on the type system. I'm going to talk about some stuff that we nabbed from Haskell that you are probably familiar with if you've used Haskell, and some stuff that we have that Haskell doesn't have as well. Okay, so I'm not going to give sort of an introductory sort of talk on PureScript. If you know Haskell a little bit, you'll sort of see what's going on with the few bits of code that I have. But the very, very high level quick summary is that PureScript is a small, strongly typed programming language that compiles to JavaScript. It's heavily inspired by Haskell, it's written in Haskell, and it's specifically designed to target the web and front-end development specifically. So you can learn more at purescript.org or on the PureScript channel on either Slack, the FP Slack, organization, which is probably the best place, and then there's a PureScript IRC channel on Freenode as well. So the goals I had, I should just say, by the way, stop me if you have questions. I don't have that many slides, so yep.
As an introductory comment, can you say a quick word about contrast with YESID, ups or downs?
Well, I can talk about pardon me, contrast with like Haskell specifically, like Haskell generally, as a language, and then I'll talk, I guess, a little bit about YESID. But so the major difference between Haskell and PureScript is that PureScript is strict, Haskell is non-strict. Okay, so that has a lot of repercussions in terms of the way you write code. If you write in a If you're writing in a strict functional language, a lot of the idioms don't directly translate over, but there's still a lot of things you can take from Haskell and bring over to PureScript and be productive. There's a few other differences. Mostly, I can summarize it as saying, PureScript was built specifically with the web in mind, right? So, it's a strict language. It compiles to really sort of readable JavaScript on purpose. Those are the main things, but I'm going to talk specifically about some of the differences in the type system in a little bit anyway. Comparing to YESID, if you're not familiar, YESID is a web framework for Haskell. You would write a more traditional sort of back-end driven, web application using YESID. PureScript tends to focus more on the front end. You can write back-end applications in PureScript, but you'd be more likely to write like a single page application in PureScript than do something like you would with YESID. Okay. Does that answer your question? Yeah, okay, cool. So yeah, please interrupt with questions because I don't have that much material to get through. So just quickly a little bit about the goals that I had in mind with PureScript. I wanted to build a language that I wanted to use every day. At the time I wrote it, I was using TypeScript and JavaScript. There were a lot of alternatives for writing strongly typed compile to JavaScript languages, like Roy was probably one of the ones that I took the most influence from. What else? So now there's things like Flow. There was Elm at the time that was just getting started, JC.js, Haste. None of them really did exactly what I wanted, so I tried to sort of piece together, the rudiments of exactly the language I wanted, and then we got a lot of contributors, and now it's obviously a much bigger language. To explore how types can improve web programming was one of the goals, to try out just some new type system ideas. One of the stated goals of GHC is that it should be sort of a playground for new type system ideas, that researchers should be able to take their new idea for a lazy, compiled, strongly typed functional language and just add it to GHC and see how it works. So I wanted a similar sort of thing for PureScript, where you could just, if you knew how to build a Haskell project, you could just sort of try something out. And make progress with ideas really quickly. And as well, just have a fun project for people who are new to open source Haskell. So if you're interested in joining the PureScript community, there's a lot of sort of small tasks that, interesting small tasks that can, to be done on the compiler. If you want to contribute to an open source, like a major open source Haskell project, there's a whole bunch we can help you get started with. basically just have to know how to build a project with Stack, and you can get started. Okay, so quick agenda. I'm going to recap some Haskell extensions that some of them are pretty common, some you might not have seen in a while, so we'll just go over them. Talk about the implementation of the type system a little bit and those features, how they get implemented just at a high level in the PureScript compiler. I'll give a couple of quick demos of some features that we have in PureScript that we don't have in Haskell. And then I'll just talk a little bit about some ideas for type system features that we would like to add, ideally before like a 1.0 release. Okay, so a few Haskell extensions, or just features I suppose to begin with. So hopefully everyone's seen type classes before. A lot of the features I'm going to talk about sort of build on type classes pretty extensively, but the basic idea is that we want to capture like predicates on types, right? So if I want to talk about types that types A that have decidable equality, right? I can test equality of two values of type A. Then I can build a type class called eq for equality to do that, right? And so I have a class called eq. It has one type parameter A, and it's built out of a method called eq with a lowercase e. That takes two values of type A and returns a boolean that tells me if they're equal or not. Okay. And instances attach basically assert that a type is a predicate holds for a certain type. Okay. So this instance called eq boolean inhabits the eq type class for the boolean type, just true and false. Okay. And it's implemented using pattern matching. True is equal to true, false is equal to false, and everything else is not equal to everything else. Okay, and one basic but really useful feature of type classes is that you can use type classes to you can build type class instances out of all type class instances, right? So if I want eq for lists, well, I can give you a quality, a sensible definition of equality for any list type as long as the elements themselves have a sensible definition of equality. Okay, so I can say that I have an instance called eq list for eq of list A. Whenever, and that's what this this arrow here means, whenever I have an instance for eq on A. Okay. Any questions on that first of all?
Just wonder, we all just got a meetup thing that someone's trapped downstairs.
Oh, okay. Okay. So just going to fly through some of these ideas from Haskell, right? So another one that we borrow from Haskell that a lot of languages don't have is higher kinded types, right? So in PureScript and languages like PureScript, you can write these data type declarations, right? Where you have a data type and then a bunch of type arguments, and then you can use them to build your data type out of those type arguments, right? But crucially, in PureScript and Haskell and a few other languages, the arguments don't have to actually be types, right? They don't have to represent types. They could represent type constructors, so they could be functions that take types to other types, as an example, right? So this is an example where A here is a type, right? So for example, I can construct this free thing with this pure constructor by just giving you a value of type A. But F isn't a value, right? F isn't a regular type, like a type of values. F is a representation of a type constructor. It takes types and gives me new types back. Okay, so I can apply F to a type and get a new type. So for example, I could apply free to list, which is not a type itself, but it's a list of A as a type. Okay, list is a type constructor. Okay, so when we have the ability to talk abstractly about type constructors or type constructor constructors and what have you, then we say we have higher kinded types, okay? Because we can classify the different sorts of type constructors using this notion called kinds.
So how do you know, looking at the signature, that in free FA, F is a constructor?
Right, so what's happening here is we have essentially type inference going on one level up at the type level, inferring kinds, right? So just like types track the types of values, just like types characterize values, int is different from string, kinds characterize types and type constructors, okay? So the kind of a list is a different thing from the kind of integers, for example, right? One is a type constructor, so we classify them with kinds. And we can do kind inference just like we can do type inference. So what happens here is when I type this declaration in, kind inference works out. Even though I didn't write this is a type constructor, the compiler can figure out, well, you applied it to a type, and you gave me back something that was in a type position, so it has to be a type constructor. Okay.
What happens if there are multiple kinds for which it would work out?
Right. So there's some extensions in Haskell, like polymorphic kinds, right? The polykinds extension, which lets you do similar sorts of kind inference, for types that you would want to do for polymorphic values. So like we can have polymorphic types or parameterize over polymorphic types and all these things. Maybe we want to do the same things at the kind level. PureScript doesn't have polykinds, but you can do some of that stuff in Haskell. I'd like to add polykinds eventually, but we don't have it right now.
So if you don't specify what kind it is, and there are multiple kinds that will work, does it just assume its kind is type?
It just defaults to star, yeah, type,
Okay.
yeah, exactly. I've tried a couple of times to get polykinds to work, but it's a little bit tough to get the details worked out. But yeah, it's on the list. So, okay, and just like, well, why do we care about this, right? Like, why this is not just like. This is actually useful, right? So the reason is we can parameterize things like classes or functions, or the types of functions, also over higher kinded types, right? So I can write a map function for arrays, or I can write one for lists or binary trees, parameterized over the types of the values in its leaves, right? They're all similar sort of concepts, and they obey the same laws, right? So why should I not be able to write one function that does, that implements all of those mapping operations, right? And I can, because PureScript allows my type class definitions to refer to higher kinded types, right? So I can say functor f, the type constructor f is a functor if whenever you can give me a function from a to b, I'll give you a function back from containers f full of a's to containers f full of b's. Okay, so I can implement this for lists, arrays, and whatnot, but I can use it generically. Any questions? So it just enables a new type of code reuse. Any questions on that?
Is that an extension necessary in Haskell? Or is that
No, that's that just comes with Haskell 98. Yeah. Okay, so the next feature we have from Haskell is functional dependencies, right? And this is one of my favorite features in PureScript because it has such like a high power to weight ratio, right? Like we didn't have to do all that much work to add it, but it enables so many things, and I'll talk a little bit about some of the things it enables. So if type classes are like predicates on types, right? Then if I allow myself multiple types,
I'm gonna parse that. Type classes are like predicates. Okay.
So we said like the eq type class is like a predicate, right? Like a type may or may not have decidable equality. Well, the generalization of a predicate on a type is a relation on multiple types. So if I allow myself multiple type arguments here, then I can talk about relations between types and between type constructors and things like this, okay? So for example, in the MTL library in Haskell, there's this type class called monad state, which allows you to talk polymorphically, generically about monad transformer stacks that support the state operations, okay? If I want a monad that allows me to get and set a piece of mutable state, that might be the state monad, or it might be the state monad transformer transforming some other monad, right? There's lots of different monads that implement that interface. And in general, we have this class to talk about them abstractly. And it's a relation between two types. Well, a type and a type constructor. Okay, so S here is the type of the state I care about mutating. And M is the monad that I'm trying to state. This monad contains this ability, right? Has the ability to modify the state. Now it turns out when you have relations between types and type constructors, it's often useful to be able to say things like, compiler, if you can infer this type, then you can also infer the other type, right? If you're trying to solve this, if you're trying to find an instance for this and you only know about M, then this functional dependency says that you can figure out S, right? If you choose an instance for M, then you can just take S to be whatever that instance said it should be, okay? You don't have to match M and S both. You could just match M and infer S, okay? So this is really powerful because it allows me to talk polymorphically about monads M, and then not worry about like having to put type annotations on the state type, because if I didn't have this functional dependency, in some cases the compiler wouldn't be able to figure out which instance in some cases. So functional dependency is like a really practical thing when you want to do things like use the monad transformer library, but they also enable a whole bunch of other really interesting things. Yep.
So if you're writing, it's only when you're doing inference that that's the case, right? If you were writing out the, because the S comes before the M, so you couldn't like just give it the M without giving it the
Yeah,
S.
so the order here doesn't matter.
Okay.
The order on the right and the arrow, right, the direction of the arrow matters. Okay. So this says M determines S.
That's for writing this type class instance, right? But if you were going to write an implementer, you'd actually have a particular S in mind. Is that what you're getting at?
I guess so.
I don't know.
Yeah, I should have probably written a little bit of code to illustrate this, but it's sort of tricky to see exactly why the compiler needs this information. But in some cases, you'll end up where you think it's so obvious that like it should have picked the monad state instance for like this particular monad, but it didn't because it couldn't, like if we didn't have the functional dependency, the state type wouldn't have matched because I was using it like polymorphically or something. Yeah, in practice, it's just really handy to be able to talk about these relations this way.
Does this state that when you create an instance of monad state that you have to bake the S into that instance or not?
Yeah, so typically you'd say something like, as an example, M might be the state monad, right? State S. In that case, I'd write something like instance monad state of S for state S, right? And the compiler might know that it's state. I'm using state of something, in which case it can infer the S must be whatever was inside state. It has to be the same one. Okay, so this is just useful for sort of, in practical terms for using things like the MTL, but it's sort of much more general than that, right? Really what's going on here is if we have a relation between two type arguments like this, from a relational point of view, what we want to be able to say is, this is actually not just a relation, but a function, okay? It's functional in one direction, in the sense that so what defines a function, right? If you have which way around is it? I'm sorry. If you have two images in the domain, no, I've forgotten. But does anybody know enough relations to complete that? I forget.
What is the question that you're trying to
so the point of a functional dependency is that like this thing that I'm defining, this class, this relation between type arguments, is not just a relation. I can say more about it, right? I can say that it's actually functional. It's a functional relation. It's a function from one type argument to the other.
Two different S's will necessarily mean two different M's.
Right. If you have the same M, you have to have the same S.
Oh,
Yeah.
okay.
The other way around, I think.
Yeah, no, opposite
If
of what
if you have 2 points in the relation and they have the same X coordinate M, they have to have the same Y coordinate S. Yeah.
Sounds like you're sneaking up on dependent types. Like, given a type, I can give you back another type.
So what I'm driving at is that like we can start doing like type level programming, right? So we don't have dependent types in the sense of actual types, depending on values, but it allows us to do basic versions of a lot of the sort of things you would do in dependent type languages, like talk about type level natural numbers, write functions at the type level to add them together, and then say things like, if I have two lists and I can concatenate them, then the length of the result is the sum of the lengths of the inputs, and write that in the type system and have it checked for me. Right. So functional dependencies let us write type level functions. Okay, so here's a little definition of type level natural numbers. A type level natural can either be 0, which is z, or it can be the successor of it can be 1 plus a smaller natural number, okay, which is the S constructor. So S of z is 1 plus 1 plus 1 plus 0, which is 3. That's how you'd represent 3 at the type level. And then using type classes with functional dependencies, right, we can write type level functions that relate relations between these things that are functional in those arguments. Right, so we can say, I have this add class that's a three-way relation between two inputs and one output. And if I know the two inputs, then I can infer the output. Okay. So to implement this, I could say, looks like I actually didn't quite finish this. This should say, if I add 0 to any n, I get n. And if I add a successor to m, then I get the successor of what I would have gotten if I'd have, just added n, right? So if n plus m is r, then 1 plus n plus m is 1 plus r. Okay, so we can just build it up inductively on the left argument. Yeah,
So that middle one is just 0.3.
Sorry, say that again?
So the middle expression is 0.3.
No, I failed to finish off the slide. It should say that. It should say if I add 0 to any n, I get the same n back. Yeah. So if this is just by sort of induction on the left argument, right? It's just proving that we can implement addition by induction on the first argument. Okay. So you can do an awful lot with this, right? This gives you like a really rich language at the type level to do some really cool stuff. It gives us, so some people call this type level prologue, right? Because if you look at instances like this, it's like saying, I have this goal, and goals can depend on other sub goals, right? And I have this tree of goals that I have to satisfy, and I'm just sort of declaratively stating, how this set of rules, and then the inference engine just figures out how the rules get put together in order to sort of implement what I
still
want.
don't understand the last statement in those 3 lines.
This one?
Yeah.
Yeah. Okay. So this is saying. So is the first one clear?
If you add 0 to n, you get n.
Yeah. So this one says if you add, so there's an implication here, right? This is like the sub goal. If this is true, then this is true. Okay. If you add n to m and it results in r, then adding the successor of n to m gives you the successor of r.
Okay.
Yeah. Okay. So this is like this is like the hello world of type level prologue, right? And you can do a whole bunch of really cool stuff. So the first application we had for it was called PureScript generics rep, which was a sort of reinvention of the generics library that we had for doing generic programming, right? If you're familiar with GHC generics in Haskell, the way it works is that you have a type class called generic, and it associates with, via sort of an associated type, a representation for that type. And the idea is that, so it reduces, so you have the types you want to program with, and then you have representations, right? And the idea is that the set of representation types should be much smaller than the set of actual types you work with in your day-to-day work, right? And if you can write...
What's the difference between a type and a representation?
Well, so just think of a representation as like a smaller set of types that sort of like represents all the types you could, so types are built out of things like sums and products and, very small set of constructors, right? Let's call those representations. If I can write a program generically for any one of the representations, then I should be able to write it for all of my data types. Right? So that's the idea with GHC generic. So we don't have associated types.
Can you give an example of that?
Yeah, okay, so let's say so take the eq type class, right, that I had before. Eq instances are often really boilerplatey, right, because you write them all exactly the same way. If the type you have is a product of 2 smaller types, then all you have to do is check that both components are equal. If it's a sum of 2 smaller types, all you have to do is check, are they both in the same summand, right? Are they both at the left or are they both at the right? And if they are, check equality on the sub thing, right? The smaller thing inside. Okay, and then I have equality for integers and all these primitive types, right? Strings, what have you. So I can just lift it up that way, right? Like if I have all my primitive types have equality and sums and products have it, then I can build up equality for all data types. So my representations are like sums and products. If I can define equality on just those, then I can map over to the representation world, write my equality instance, map back, and now I have an equality instance on my actual data type, right? So that's GHC generics in a nutshell. We can't do GHC generics in Haskell, in PureScript, because we don't have associated types like we do in Haskell.
What's an associated type?
An associated type is a type class that has a type like associated with it, right? So, sorry, a type class whose instances have types associated with them. Okay?
Can you give an example of that?
No, it's not really the point. The point is functional dependencies allow us to express type functions, and that's enough to be able to do generics rep, because I can express the mapping from types to representations as my type function.
That type function, is that just expressed as like a constraint?
Yeah, exactly. So we have a two argument. I mean, I can show you the code.
Can you just go back a slide or two? Slide. skipping slides that I realized was constrained.
Yeah, sorry, just one sec. Generic. So this is the definition of the generic class, okay? It has two arguments, an A, which is the type I care about, and rep, which is the representation type, and a functional dependency which says, if you know the data type, you know the representation, okay? And then we have two functions here to go back and forward, right? From the values to the representation of those values and back to the original values. So if I want to define an equality, well, what's a good example? In this module, I have generic equality defined, okay? So I have this other type class called generic eq, and then I have this one implementation of equality that says, if you have a type A that's generic with a representation, and the representation has generic equality, then I can implement equality for the thing you first thought of, right? So then, you know, there's a whole bunch of these things, right? You can implement show this way, you can implement monoid, semigroup, odd instances, all sorts of stuff.
So is your representation, is that purely at the type level, or is it a proxy, or is it some value that represents the representation?
They have inhabitants, yeah. Yeah. So if we go back to the first module, so here are some of the representations, right? No constructors says I don't have any constructors. No argument says, you know, I have a constructor, but that constructor doesn't have any arguments.
So
Sums of types, product of types. Yeah.
Is there any reason that I mean, because obviously you were talking about how there's no associated types, so you can't have like the type representation, but couldn't you have a just using functional dependencies, could you encode that exact same thing instead of using type families, using functional dependencies?
Yeah, that's how we do it.
Well, but the thing is that in GC generics, isn't all of GC generics just at the type level? There's no inhabitants for any of the types, or it could just be totally uninhabited types.
I think they're inhabited, yeah.
Yeah. Okay. Then I just don't know about GC generics.
So I did think about doing it that way. The problem is we don't have GADTs, right? Because what would be really nice is if you have like a kind of representations, right? And then you have the shape, just the shape, no values. And then you have a GADT, which essentially acts like it's singletons or whatever. Then you can just talk about the shape, which means you can do things like hash the type without having to have a value of the type around, things like that. I suspect you can probably do that anyway. But anyway, so the major application of this initially was generics rep. But now there's a whole bunch of like really interesting applications using this for all sorts of interesting stuff. So two of these, for example, by Liam Goodacre. The first one is PureScript type map, which is a full implementation of the maps library from PureScript, like the dictionaries. So balanced 2-3 trees implemented at the type level with functions like insert, delete, rotate, expressed as type level functions with functional dependencies. And then if that wasn't sort of crazy enough, then typelang is a full interpreter for the simply type lambda calculus implemented inside the type system using functional dependencies. And there's a whole bunch of these, right?
What happens if you make the type checker go into an infinite loop?
It tries. It basically has a maximum sort of depth in the solver, right? So if you get to 10,000 depth, number of sub goals it's tried, then it just gives up and gives an error. Okay, so the next feature we nicked from Haskell is higher rank polymorphism. So you might have seen types like this in Haskell, for all A something, like the identity type for all A arrow A. So higher rank polymorphism says, why don't we make that into a type in its own right, where we can put it anywhere inside a type, right? So not just on the outside, for all can appear inside types, right? So for example, one application of this in Haskell and PureScript is the ST monad, which is a state. So there's a paper that goes with this called lazy functional state threads. And it's basically an alternative to things like the state monad for tracking mutable state, but in such a way that the type system lets you know that the mutation can't leak out of the function you're trying to define, okay? And the way it does that is to use higher rank polymorphism, okay? So in the type of run ST, we can think of STHA as being a computation of a value of type A, where I'm allowed to do mutation inside a sort of conceptual heap of type named by this type H. Okay, and the type says I can remove the effects, right? I can let you get hold of an actual pure value of type A, as long as the computation is polymorphic in the actual heap. If you can sort of go and do your mutation, go and do the work, but you don't know like which part of the heap you actually mutated. Like if you're unaware like where the mutation was happening, then I can safely remove the polymorphism, because you can't, this type variable can't leak out, right? You can't say, you know, for example, pass out a mutable reference to a value, right? This monad lets me sort of create references to mutable values, read them, write them, modify them, but this heap parameter gets tracked inside them, right? So I can let pure values leak out, but because this is polymorphic, I can't let references leak out, and that's why it's safe. Okay, so there's lots of neat things you can do with this. Another another cool thing you can do with this is sort of information hiding, right? So this is a little bit like existential types, if you've heard that term, right? So suppose I have some interface, and I want to give you an implementation of that interface, but I don't want to tell you what the type was that implemented it. Okay, so I can say, well, if you know, for any result type, I'll give you a result back if you can tell me how to produce a result for any choice of implementation. Okay, but you don't get to use knowledge of the implementation you know, outside this function. When you pass me this function that computes the result, you have to use it abstractly. I'll give you some interface with which to compute it, and I'll give you a proxy for the actual implementation type, but because it's polymorphic here and not on the outside, you can't use that information in the, you know, to influence the computation. Does that make sense? It's sort of, this is a very, very high level summary of, like, you know, an entire Haskell extension. So
how would that be different from having the type constraint outside of, like, the first thing in your type signature?
Right, so if I said for all result and implementations, interface, impl, and then everything else was the same, right? So in that case, you know, I could call, well, so for a start, when I call this hiding function, I need to know the implementation, right? But I don't want the caller to pick the implementation. I want the function itself to pick the implementation. But I don't want you to know what implementation I chose. Yeah.
Do you also allow that for all in positions that expect a type variable for something like proxy impl? Could that? So
like in predicative types, yeah, we do, and don't tend to talk about it too much because it usually, like, things just go badly wrong. But not like it's not like you get bugs in the code, or like it's not. I don't think it's unsound, although I'd be interested if somebody like showed that it was. It's just type inference is terrible, so we don't tend to use it that way. But but there's no sort of syntactic restriction stopping you from doing that. So the question was, can you say things like array of polymorphic type, right? Can you have a polymorphic type inside a type constructor? And the answer is yes, but you probably don't want to. Okay, so next section I'm just going to talk a little bit about implementation of the compiler. Are people interested in hearing about the implementation of the compiler generally? Like, yeah, all right, cool. Any questions on the stuff so far? No? Okay. All right. So yeah.
So how exhaustive is this list of features? Is this kind of?
That's a pretty much a complete list of, you know, the really interesting stuff we took from JC. There's more features that I haven't talked about yet that we have that Haskell doesn't have, and there's lots of features that Haskell has that we don't. Like, we don't have GADTs, we don't have type families, and we don't have polymorphic kinds, right? This, I think it would be nice to have some of those. I find this is like a really nice set of features for doing, you know, pure functional web programming, right? So if we don't add those features too soon, I wouldn't be, you know, it's not the end of the world. Like, I think we have, especially functional dependencies, I think, like I say, adds a lot of power for quite a small feature. I quite like the set of features we have at the moment.
I'm curious about, you know, when you're building a language and a compiler, that has a community of people that are using it. I'm curious what your decision-making process is when you decide, what am I going to prioritize adding to it?
Yeah. So, like I said, I want it to be a little bit of a place to try out new ideas, right? So to a certain extent, I don't want to throw out ideas because they're like too crazy or something, right? Like we should, but on the other hand, as soon as you add a feature, somebody will go use it to make a library, and then you can't remove it, right? So, so I don't really have a great general answer to that. Just if something seems like it has, it's going to be useful generally, we'll discuss it. We have, a lot of the contributors will like get involved on the GitHub issues and say, I'd use it for this. I think this is, a bad feature, whatever, and then we decide whether to merge it or not. And we have, the issue tracker just generally tracks stuff we're interested in implementing, and then, it's unusual that somebody just comes along and like, look, I made this feature, like it's fully formed, ready to merge, right? Yeah, so usually like people have an idea of the sorts of things we're interested in. Does that answer your question?
It does. I'm just very curious coming from, I'm more used to focusing time on developing a product that has a very explicit set of users.
Right.
Where any sort of problems that they have is communicated to me very well, versus, for me as a user of the language, I may never bring up any issues that I have, and it's tough for maybe people contributing to the language to be aware of it. So I was curious, just as a general question, how you go about, building a language meant to serve all kinds of people, many of whom you may not know exactly what they're doing with it. So
yeah, I mean, I had a general idea when we started the project of like, these are the features that I want to have, and it was actually pretty small, and I'm pretty sure like I have all of them at this point. Like I wanted algebraic data types, and I wanted a way to write pure functions, and write small data structure libraries. And that was, the initial goals were pretty small, but now people use it for sort of full application development, right? So like the goals have changed a little bit. So it's sort of, it's a fluid thing, and it changes over time. But we have some sort of guiding principles, I guess. If one of the major, like as an example, one of the major features of the language is that the generated JavaScript is readable and compact, and any feature which produces bad JavaScript, which is like hard to read or whatever, like we'd think pretty hard about including something like that, or so we have these sort of general principles, but generally it's just we consider each thing as it comes along. It's not like we have a massive set of contributors anyway, right? So yeah.
Well, thank you for sharing.
Of course. Okay, so a little bit about the implementation. So the type checker at a very high level can be summarized like this. Okay, what is a type checker? First of all, it takes a representation of syntax, and it tries to figure out what it means. Right? It tries to infer types, where type is an approximation to some sort of meaning. It goes and it takes every subterm of that piece of syntax, and it tries to figure out what the type of each subterm is. Okay. And then hopefully at the end, the type checker says, I was able to figure out types for all the subterms, your program's good. Or in some cases it'll say, I figured out some types, but these two types are incompatible, this is a bad program, right? So how does it implement that?
So the only two things it'll do?
I mean, at a high level, I suppose. I mean, there's a lot of different types of errors, but essentially it boils down to, are the subtypes of this program compatible with each other? Right? Like 1 plus hello is a bad program because 1 is, I expected an int, but I got a string. Okay, so at high level, the first thing we do is we go over the syntax, and we check or infer types and gather constraints, right? So by looking at a small part of the program, we can't figure out exactly what the type of that small part of the program is, right? So we might not be able to figure it out, but we can gather constraints as we go, and hopefully by the end of that process, we have enough constraints that get solved to give an answer, right? So we do that, we go over the syntax and we gather constraints, and the second step is that we solve the constraints, which I'll talk about in a second. In the process of solving the constraints, you might learn new information. For example, a functional dependency might fire and say, I knew this piece of information, and the functional dependency told me this new piece of information. That's a new constraint you can feed back into the constraint solving program, right? So you loop until there's no more constraints that can be solved. And then at the end, you have to do a little bit more work because there's various things you have to check, invariants that didn't get broken, and we do this process called generalization, which basically means any unsolved types become type arguments, new type arguments, and any unsolved constraints become constraints on the type of the inferred thing. Right, so generally, gather constraints, solve constraints in a loop, and clean up is the high-level version. Yep.
So from like this high-level overview, this sounds very much like a Haskell-style unification algorithm, where you generate equality constraints.
Yep.
But are you talking here about like type class constraints in that sense, or equality constraints in the sense that like A unifies would be?
So there's two types of constraints. There's the two you mentioned, right? And they sort of solving them has to be interleaved, right? Because functional dependencies take type class constraints and might give us new equality constraints. And if I have equality constraints, that might give me a new piece of information that I can use to solve a type class constraint. So they influence each other. And but yeah, there's two types of constraints going on. I'll talk about both briefly. What's time like? Oh, wow. Okay, let's speed up a little bit. Okay, so unification. So like I said, local information about a program doesn't give us enough to solve the type for that piece of the program, right? We might need to take partial information from different parts of the solving process and glue them together, and that's what unification is about. So unification says, if I have these two approximations to a type, can I join them together to give like all of the information combined, right? So, for example, if I have if I know that these two types are equal, something that I don't know, a function from something that I don't know, so integers, okay, and a function from strings to something else that I don't know. These are different somethings, right? And I know those two things are the same. Then I know that the answer, both of these types have to be equal to string arrow int, right? The only way you can have two functions be equal is if their codomains are equal and their domains are equal, okay? So this one has to be string, this one has to be int, and unification is an algorithm that solves that general problem, okay? So the most basic form of stuff we do in the type checker is go and get constraints like this, figure out things like, I'm not exactly sure what the codomain is, I'm not exactly sure what the domain is, but the codomain is int, or this one, right? And then the solving process takes these and uses unification to solve those constraints. Okay, so unification happens when we learn that two partially known types must be equal. So these are partially known types, and if they're equal, we can figure out the whole type. We might not figure out the whole type in general, right? It might be that this one was also unknown. This might be question mark 3. But I still know the general form of the solution is string to something, right? Okay. So really quick example of how you would do type inference, right? Let's say I have a function test. Test of f of x equals f applied to x again. Right, that's a PureScript program. How would we figure out the types of the expressions, right? So the first step was to go through and gather constraints. Maybe I can move this a little bit. Can everybody see that enough? Sorry. All right, so let's gather constraints. So we'll start off by giving these things names, right? So I'll call this thing, the type of this thing alpha, f is going to have type alpha, x is going to have type beta, right? And let's look at some subterms. Well, so function application parenthesizes like this, right? F applied to x, applied to x, right? So if I'm applying f to x, then alpha, which is the type of f, must be equal to a function type, okay? And it takes x as an argument, and x has type beta, so its domain must have type beta, okay? and it must return some other type, but I don't know what the other type is, so I'm just going to make up a type variable. It's called delta. Right? So I have one constraint now. Alpha, which is the type of f, is a function from beta, the type of x, to some other new type delta. Okay? I didn't use gamma. Let's call it gamma. Okay? So now I know that the type of this thing is gamma, right? That's the type returned by the function application of f. Okay? And now I can do the same thing, right? Now I'm applying something of type gamma to the type of x. So that also must be a function. It also must be from beta. And its return type is the return type of the whole function, right? So let's call that delta. Okay. And test, the type of test is, so delta is going to be the return type of test, right? So test is going to have type alpha to beta to delta. So the first stage might go through and like produce that list of constraints, okay? The second stage says we need to solve those constraints, and you can solve them just by substitution like you would in like linear algebra or something, right? So go one constraint at a time and just substitute them into all the other equations. So cross that one off the list. Alpha is beta to gamma, so I'm just gonna modify this in place. Wait, was that? Yeah, good. Beta to gamma. Test is, no, I got that wrong, didn't I?
I think you replaced beta with the.
Yes, I did. Thank you. I really shouldn't do this in place. Let's do it properly. Okay. Quick check. Beta to gamma, beta to delta, alpha to beta to delta. Okay. So when we solve, we'll get gamma. So the second version of this says alpha is beta to gamma. So then we only bother substituting into this one. So we can replace that with test has type beta to gamma to beta to delta. Okay, and then let's cross this one off the list, right? So gamma is beta to delta. So the third version of this is test has type beta to delta to beta to delta, and that's correct, right? Now we don't have any constraints left. That's the most general type of test. Okay, so that's unification, solving, type inference by unification in a nutshell. Go through, generate all the constraints you can figure out, and then just substitute your constraints into each other until the only thing that's left is the thing you wanted the type of, and then that's your answer. Okay, and anything. So when I said generalization before in step 4, right, a cleanup pass and generalization. Generalization says anything that was left over that you couldn't figure out the type of is universally quantified. Beta and delta. Right. So test has type for all beta and delta, beta to beta to delta to beta to delta. Okay. Does that make sense? A bit rushed. Little overview. All right. Nope. Yeah, okay, that's unification. All right, so unification is sort of the heart of the type checking algorithm in PureScript, okay? But in order to implement some of the features that I talked about before, type classes, rank n types, sorry, I called it higher rank polymorphism, we need to do something a little more interesting, right? So here's the way I think about this thing called bidirectional type checking, okay? If you're going to add features to your language which break type inference in the sense that not all programs can be inferred, right? Then, so if we only had basic functions and applications, simply type lambda calculus, right? Everything has a principal type and everything's great. If we want these features, the price we pay is that we pay a price in terms of inference, right? We can't, type reconstruction becomes undecidable when you add certain features, okay?
Type reconstruction?
So type reconstruction is the process of going from syntax to types, right? That's an algorithm. It's decidable for simply type lambda calculus and other things, but it's undecidable when you add certain features like rank n types, okay? The answer is that you need type annotations, right? If you make the trade-off to add these features, you're going to lose type reconstruction. Right? So the only way to solve that problem is to add type annotations to your program to give the compiler help. Okay. If you add type annotations, you have much more information to use, right? You don't have to go generating constraints. Not everything has to be done by generating constraints and then solving everything at the last minute. If you have type annotations, you can split your type checker into two modes, right? If you have a type annotation, it's easier to check that a term has a type than it is to try and guess what the type was and then check that you guessed the right type, right? If you don't have a type annotation, you have to fall back on inference, right? That's mode one. No type annotation, you just do type inference. If you have a type annotation, it's better to check that the type annotation is correct, okay? Because it'll give you more information to check with. So that's the way I think about this thing called bidirectional checking, where, and the gist is that you split your type checker into two functions, or two judgments, inference and checking. So inference is used when you don't have type annotations, checking is used when you do. In practice, we have a couple more. The function application judgment is used whenever you have a function application, and that is an application of a function to something else.
Is that tricky?
No, it's just these things all sort of depend on each other in sort of interesting ways, right? The type inference algorithm is basically like choosing which judgment to use at which point in the code, right? And they combine in interesting ways. I'm just saying, it's not just inference and checking. You can write a type checker that just uses inference and checking. We need a couple more to implement everything we need. The interesting one is called subsumption, which says it's a relationship between two types, and it says basically that one type is more general than another type. Okay, so if I might get into a situation where I inferred one type, but you gave me a type annotation anyway. In that case, those types don't have to match exactly, but it better be the case that I thought of something more general than the type you wanted. So that's what subsumption does, okay? So bidirectional type checking is basically, these two things. But in practice, we have a bunch of different judgments, and they all sort of like depend on each other in a bunch of interesting ways. And at the bottom, when you get down to simple types, it basically boils down to unification, and that was this, right? So that's the algorithm in a nutshell. And there's a couple of interesting details, right? So there's this thing called scholomization that we need. So when you check something has a polymorphic type, as often comes up when you're working with rank n types and things like that, you need a way to represent so let me just go back a second. So when I talked about higher rank polymorphism, right, I said the reason this worked was because you had to be polymorphic in the part of the heap you were using, this sort of like conceptual representation of the heap. And here I said this is safe, or this, the implementation is hidden because you had to work with any implementation, right? Your function had to work for all implementations. So I need some way in the type system to represent the fact that this implementation type is like some hidden thing, right? Or this heap is some hidden thing that you're not allowed to leak into the surrounding context. So that's where scholomization kicks in, right? That's what that's useful for. So let's say I have this type and I have this term. Lambda x goes to x, right? Lambda x goes to 1, right? This has this type, right? This checks against this type. The function that takes x to x certainly takes any a to a. But this function, lambda x goes to 1, doesn't have this type, right? Because it certainly takes any type a, but it doesn't return that same type a back, it returns integer, right? So the way we check this is to use this concept called scholomization, right? When checking something as a polymorphic type, we need to generate a fresh type variable which does not unify with other types, right? It can't be made equal to other types, and those are called Scholem constants. And part of the cleanup process is this idea of checking that Scholem constants can't escape, right? So to give an example, we have to check during the escape check that this H didn't leak into the outside context, i.e. you didn't leak any mutable references into the outside context, or this implementation didn't leak out into the result type. Okay, so to check this...
So when you check that there is no leakage, is that the compiler checking its own work or checking the programmer's work?
That's the compiler checking the programmer's code, yeah. So just to illustrate this quickly, if I want to check that lambda x goes to x, checks against type, I'm going to write it this way, for all a to a, then the rule we use says we scholemize this polymorphic type, right? So I replace a...
Wait, I'm getting lost if that there exists.
Yeah, so I'm going to have to write it a bit bigger, I suppose. Okay, if I want to check that lambda x goes to x, has type for all a arrow a. Okay? Okay, so the rule says I have to replace this for all, get rid of the for all and replace the a inside with this column constant. Okay, so that's true, writing it in a sort of natural deduction style. If for some fresh column constant, which I'll write over here, so I'll generate a column and I'll call it, I don't know, star or something. Lambda x goes to x, checks against type star to star for some fresh column constant star. Okay. And in order to do that, we can check that, well, I guess we need a context. So we can check that the result has type.
What's that symbol you got on the left?
This, I need to sort of keep track of the variables that are in scope, and this is the way we write it in when we do. If you read type checking papers, you'll find it's often written in this sort of natural deduction style. This represents a context, so it's a collection of type variables that are in scope. This turnstile means entails or something along those lines. So, or in the context gamma, it can be proven that such and such has type such and such if the thing above the line. Okay, so if I can check that x in the context gamma, in the context gamma augmented with the assumption, right? This is the checking rule for functions, and then I just use
this. I don't know what you were waving at.
Sorry, I should probably just skip this. Sorry.
No, don't skip it.
Okay.
I'm still running it.
Okay, so this is like a compact notation for the algorithm that the type checker implements, right? Every step from below a line to above the line represents forward progress in the type checker, right? There's a lot of rules in the type checker that say things like, if you want to check that something has a polymorphic type, scholemize the type and check the scholemized type instead. Right? That's an actual pattern match that exists in the compiler somewhere. And then there's another one that says, if you want to check that, this is called something like check a function or something, right? If you want to check that a function has a function type, then check that the result type has the result type in the context augmented where the name that you bound on the left-hand side of the function has this type. Right, so I moved this assumption into the context, and then I check that the result has the right type. Okay? And then finally, there's the variable rule that says if you have something in the context, you can just use it to prove what you want to prove, right? So of course I can prove x has type star in the context that tells me that x has type star, so I'm done. Good, right? That's using scholemization to check, this. But if I go through and I replace, my other example was a bad example, right? This obviously is not going to work, right? So we just plumb everything through. Now I said the result has to have type star. Okay. So I can try and use this rule. Sorry, I don't even have to try and use that rule, right? I can just say, if I have some rule for integers or something, 1 obviously has type int. And I can check that, I said column constants don't unify with anything else. It can't be made equal to int. So that's a type error. So column constants have two properties. They can't unify with anything except for unification variables, which have to unify with everything, right? So they unify with the absolute minimum set of things they could possibly unify with. And they're not allowed to leak out of scope. So we have this concept of scope that I talked about earlier, where, you know, my syntax, every piece of my syntax, you know, is associated with a certain piece of scope, and a for all introduces a new scope, and part of the cleanup operation that I have to do at the end of type checking checks that this H didn't leak out of that scope.
Do you have an example of a type where the type checker might complain about something escaping its scope?
It's tricky to come up with one. I wish I'd prepared one. So the usual example is something like run st applied to something where you leak a type variable, right? So if actually I can give you an example. So you can write this in Haskell, right? Run st new stref 1 has an escape type variable, right? Escapes column, sorry. Right, because I created a new stref and I tried to have it leave its scope. The scope is this part of the program, right? So I have to check. So when I'm checking this, I get into checking mode here, right? Because I applied a function to this thing. So I check that this has type for all h, st, h, a. Okay. So I'm checking something against a polymorphic type. I have to scholemize it, right? So I say, check that it has type st star a, where star is a new column constant. Okay. Well, new stref has type, what does it have? It has type a to sth stref h a. Okay. So I have to check that.
You're missing a for all.
Yes, I am. Thank you. For all h a.
Now the type you wrote below is the type you know this has because it's an argument of run st.
Yes.
Okay.
So let me get this the right way around. This has to, one of these has to be more general than the other. Sorry, I wish I'd have prepared something for this. Anyway, the point is, this type A ends up becoming stref HA, okay? And then when the escape checker like looks at the type of this thing, it says that's stref HA, but this is the scope of H. H appeared outside its scope, so it got a scope leak.
So to be clear, because I'm pretty sure my implementation of escape check is totally broken right now, so I want to ask this question while I have you in the room, which is basically, so the scope that you talk about, like that syntactic, is that based on the syntactic type or the syntactic expression? Like, is it delimited based on where the for alls are?
It's where the for alls are.
Okay.
Yeah, and I never particularly liked the implementation I have of scholomization, especially the escape check. It's kind of really messy. You don't have to do it this way. Like, another way to do it is when every time a unification happens between a unification variable and a column constant, you just sort of like write it into a log, right? And then your scopes become ranges. So in addition, what you do is every time you check something as to polymorphic type, you remember which unification variables you saw during that period, and that's a range, right? And then you look at your log at the end and you say, did any of these unifications fall outside that range?
And that gist you linked to me a while back.
Yeah, does it that way. And then the other way you can do it is to not use scholomization at all, which is what the complete and easy rank-n types paper does, where the context actually tracks, scope implicitly. Okay, pressing on. All right, type classes, right? So very quick version of what we do for checking type classes. We can think of type classes as elaborating to dictionary passing style, right? That can be our semantics with a type checker. Okay. Every time we see something where we have to apply a polymorphic function that has a type class constraint, we can just insert a placeholder for a dictionary that we need to figure out later. Okay, so if I have a quick example, class show A, so this is, this is the same as in Haskell essentially. Well, not exactly the same, but I have this class called show A, and it has a function that allows me to turn an A into a string. Okay, so we have that same function in Haskell. So let's say I write a function called shout, and it takes an argument x, and it's implemented as show x plus plus some exclamation points or something, right? Okay, so let's so when we check this function, when we type check this function, right? Let's say we get to here, okay, and we look at the type of show, and it says that, like, this is a class constrained function, right? So the actual type of show is show has type for all A. Show A implies that we have a function from A to string. Okay, and there's another type checker rule that says if you try to apply a function that's constrained, then just insert a dictionary that's going to be a placeholder for like the dictionary passing style we're going to elaborate to. So this elaborates to shout x equals show applied to a dictionary applied to x plus plus some exclamation points. Okay, so after type checking, so type checking is not just a predicate, right? Like, it doesn't just tell us this is okay or this is bad. It actually is a transformation on source programs from the source code you gave me to the thing that has type class dictionaries all the way through it, right? So some of the type judgments tell you how to insert type dictionaries. Right? So we replace it with this. This has been elaborated.
Question. Where does the dict come from? Should that be a parameter on shout? Should it be shout x dict or dict?
So we can think of it as like a regular type. Like, in the generated code, it really is like a function application. Like, it's just another. Now we're applying function, show to 2 arguments instead of just 1. But there's type information in here, right? So like, this is going to end up with the type, like, for all A, it's going to have this type, right? And it's going to be this A that we need a dictionary for show for in here, right? So in reality, there's type information hidden inside this placeholder, right? And then during the solving phase, another thing we do during the solving phase is to solve these placeholders for actual dictionaries. We go through all of the instances that could possibly replace that dictionary and pick the one that makes sense based on the types that we have. Okay. Is there anything? No. Any questions on that?
If you have multiple choices, do you throw your hands up in the air?
So right now, I have a slide about what we want to do with overlapping instances. But right now, we just give a warning and say this is the one we picked, which, it's not ideal, but we don't tend to have that many overlaps. Functional dependencies implementation is basically just a slight modification to the instance solver that replaces these dictionaries. Okay, so I said that functional dependencies imply, the solver loops until there's no more constraints to be solved, right? On each stage, we solve at least one constraint, and new type information becomes available, right? So every time we solve a constraint and we get new type information, we go through and we update these little placeholder types inside our, dictionary placeholders. And then hopefully on the next turn, this one will have its turn to get replaced with an actual dictionary, right? Until the solver stops and everything's been solved, or we find something we can't solve. That's sort of the gist of the functional dependencies implementation. I was going to go through an example, but it's not particularly interesting. Okay, so I already talked about the cleanup step a little bit. The column escape check I already mentioned, and then generalization as well. So, introducing the for alls that we need for any type variables we couldn't solve, and then if there's any constraints we couldn't solve and we didn't have a type signature, we can add the unsolved constraints as constraints on our inferred type. Any questions on that? Nope. All right, just quickly talk about a few novel features we have. I've been talking for an hour, so try and get through this reasonably quickly. Okay, the biggest thing that we have that Haskell doesn't have, or at least right now, it might get it at some point, in some future version I suppose, is row polymorphism. Okay, so row polymorphism, the easiest way to see the value of row polymorphism is to just show a quick example. So JavaScript has objects, right? And objects have multiple properties. They are mappings from the labels that object has to the types of the values in those labels. Okay. One way to talk about objects is to use subtyping. And we don't do subtyping because its type inference properties are a little tricky, and the other reason is because we have row polymorphism, and there's a lot of neat things you can do with row polymorphism. So suppose we want to write, this is a valid PureScript program here, right? So a getter for the foo property on a record. So getter of a record is rec.foo, right? So it's just like JavaScript. You can just say, you know, object.property. What type does this have, right? So it certainly takes an object as its, oh, I should say this is the inferred type, right? You don't have to add this type annotation. One nice thing about row polymorphism as opposed to subtyping is that type reconstruction is possible, okay? So it certainly takes an object as its input, and it returns some type A, and the object that it takes in has a foo label with A in that label, okay? But there's nothing to stop us passing in an object with more than just a foo property, right? I can say getter takes a record with a foo property and any other properties, and gives me an A, okay? And the quantification over this R thing here, right, is quantification over a row of types. So a row is a mapping from labels to types, okay? So the ability to quantify over these rows, like these tails of object properties I don't particularly care about right now, is called row polymorphism, okay? And just like we can do getting properties, we can also do updating or setting properties, right? So if I give you an A and a foo that, you know, a label, an object that has a foo label with an A in that label and any other properties, then I can give you back something of the same type, right? But crucially, the tail is the same type, right? The type of the tail didn't change. By updating foo, I didn't update bar or remove bar or add bars or anything, okay? So this is quite handy, and it's a really nice fit for JavaScript records.
Question.
Yep.
Couldn't you actually generalize setter a little bit more to have the second argument?
Oh, actually, yes. So that could be a B and that could be a B, right? Yeah, you could. And I think the inferred type actually is that. Maybe I'll do that at the end. Okay, so like I say, it's a really nice fit for objects, right? We can talk about the labels and types that an object has, but it also is a fit for a lot of other things. So here's one thing we've had in PureScript since pretty much the beginning, since we added row polymorphism, which is extensible effects. Right, so instead of talking about mappings from labels to types, I'm going to talk about mappings from labels to effects, where effects are just type level tokens that can track, you know, the side effects I have in my program. Right, so if I have this function get from network, which like goes out and gets some resource from some network device, right? I can say that's an effectful thing, right? It returns some X. But it's effectful, so I'm going to use this f monad to track the effectfulness. And I'm going to track it with this row of effects. Right? So I'll say, get from network can operate in any effectful context that supports network operations, but I'm also going to let you use it in contexts that support other effects. Okay? Just because you're doing network effects shouldn't preclude you from doing non-network effects. Okay. And then when I use this in main, for example, I can use this alongside, let's say, log show, which prints out that network result. Okay. And that gives me a console effect. So log show gives me a console effect, and get network resource gives me a network effect, and unification joins the rows together. Okay. So because we have nice inference properties for rows, it means we have inference for the effects that our main program has. So you can think of F as being a little bit like Haskell's I/O, except for that we're tracking this, exactly the set of, things you're actually doing in main. Not exactly, but, an approximation to the things you're doing in main. And I can cut this off, right? So this one is polymorphic. I said, you're also allowed to run this computation in contexts that support other effects. But I don't want that for main, right? I don't want to say, oh, and main can have any other effects. I want to say, no, main has exactly this set of effects, right? I don't want to know that launch the missiles happen to be an effect in main, right?
What if you wanted to say it writes to the console and it reads from the network? Can you do that?
Yeah, so you can. You have to sort of refine your effects into smaller sets of behaviors. So you'd have different effects. You'd have like a write effect and read effect, and we do that in some libraries like the React bindings. It's important in React that you don't update state in certain lifecycle methods, for example, or props or something. So we use this to make sure you can't do that. There is a bit of a drawback though. There's this sort of like open world assumption with effects, right? Anybody can come and define a new effect anytime. There isn't like a closed world of effects. So you have this sort of problem where how do you decide on like what the set of effects should be? And how does it mix with the sort of open world assumption? It's generally a bit, that's the major downside as I see it, this. But there's other approaches to extensible effects that you can do in PureScript with raw polymorphism that do it properly.
So
like
what you're
PureScript. Sorry, go ahead.
about the open world problem, does that mean you could write a function that says this only writes to the console and has other effects?
Right.
Someone makes another effect or another, I don't know what you call it, that involves
so the
writing
problem,
and reading to the console?
So the problem is, right, like I write my libraries and I use the console effect, but then you might come along and say, but I want to separate into read and write, so I'm going to make my own effect. But now if a caller uses both of our libraries, they need to know about both of our types of effects, when really we're both talking about the same console thing, right? So that's the problem with the open world, nature of effects, is that you have to have this sort of like global, you have to like coordinate amongst all developers to make sure you only use this set of effects, right? Which is obviously not very practical. But in practice it tends to work quite nicely. So
I have several questions.
yeah.
The console has type console, network has type network.
Yep.
Pass to F. What is that structure?
Yep. So this is so notice here you have curly braces, right? This is syntactic sugar. It elaborates to a type constructor called record applied to a row. Okay, and this is a row, right? So I could have written what I had before by saying record and then the exact same thing, but in parentheses, not in curly braces. So this is a row of effects, right? There's a kind called effect, and console and network have kind effect, and then this thing is a row of effects. And F is a type constructor that takes a row of effects and a return type and gives me a type.
And an effect is
It's just a token. There's no like runtime representation. It's like a singleton.
Type classes. It feels like saying as long as you have eq, I can do this. You're saying
It's a little bit like
console here, I can do log show.
it's a little like, so it has some similarities with like MTL, right? Where you have like monad state, monad error, whatever, and constraints bubble up to the top, right? But so it's different in two ways. We're using rows, obviously, and we're using unification on rows to do something similar. But also, this is just a phantom type, right? There's no runtime representation of this. There's no dictionary passing going on for MTL classes or anything like that. And the reason is it all gets, eventually at the end of the day, all we're doing is we're just trying to run JavaScript functions, right? And JavaScript functions have, any effects, right? Any effects supported by the JavaScript runtime. And we're just trying to partition those up. It's just a phantom type that sort of partitions it up and says, I'm only using this subset. Yeah. Okay. So how do you implement row polymorphism? Well, I already said rows are maps from labels to types. And actually in the compiler we implement them as association lists. They are kept in sorted order. Right, so if you want to unify two, if you want to unify two rows, you can basically just do like the merge portion of a merge join, right? You keep them in sorted order, and then you go through element by element both of the rows, and if you see two labels that are the same, then you unify the types that are associated with those labels. If you see one that's in one side but not in the other, then you push that label into the tail of the other one, and hopefully that tail, was a type variable or something, right? So for example, if I have this console here and I have to unify the type of get network resource with this some type that involves this row, right, which involves console. So console doesn't appear in this row, but it's polymorphic in the tail, so I can always just push the console constraint into the tail, right?
So question, the tail you could replace instead of writing like network console, you could say network pipe parenthesis console
yes.
and parenthesis.
Exactly.
Okay.
Yeah. What did I say here? Unification of rows must ignore order of different labels. All right, so actually, it's sort of a technicality, but the rows that we have allow for duplicates. So we keep things in sorted order inside the compiler for a row, but when we have duplicate labels, we have to make sure that we don't reorder the duplicates, because the order is important for duplicates for the same label. For example, if I have effects and I want to track the fact that I can throw two exception types, it's important to remember the order in which I'm going to catch them, right?
The duplicate labels, do they have to have the same values?
They have to. They'd have the same label. They can have different types inside.
Yeah. Types.
Yeah.
So in the getter and setter example, there's a implied ordering here?
Yeah. All right, let's go back. So here you're saying that I could have a foo inside R, right?
Yeah.
Right. Yeah, you absolutely can, right? So then you have to answer the question, what is the meaning of a record, right? Given a row of types, I have some meaning that maps rows of types to subsets of values that exist inside the JavaScript runtime, right? And the meaning that we give to records only considers the first occurrence of a label, which means that you can't type, is it deletion? One of the things that you might want to do with records, you can't give a nice type to, unless you have like some sort of constraints on your rows. But is it addition? Oh, okay. Oh, like pure addition, not like updating.
Because it only takes, you only have one label or one value at a specific label. If you want to add one, you have to first check that it doesn't already exist in the record, because if you just indiscriminately extended it, then it would think it still had two labels, but you only have one.
Yeah, that sounds right. Thank you. Okay. Cool feature number 2 is row constraints. So we have a few different types of row constraints. The first one is union. Basically, I'll just sort of run through this real quick, but union says it's a three-way relation between 3 rows, and it basically says that the third one is the union of the first 2. So why is that handy? Well, it lets me type things like joining two records together and just keeping all the keys, right? And there's an implementation of this in this PureScript records library, and I wanted this feature ever since I saw it in the Ermine compiler. So we sort of nabbed the idea a little bit from there. I don't believe they have duplicate labels, so it's a little bit different, but the idea is essentially the same. What's it?
Which compiler?
Ermine. It's S&P capital IQ, I think, right? Develops it. Compiles to the JVM, I believe. And they have row polymorphism as well, and they have these nice row constraints. So it lets you give nice types to like joins, like relational joins and things like this. Ours is a little different from the one in Ermine, but the concept is basically the same. So this is sort of illustrative of like a general thing that we're tending towards in PureScript, right? So we have 2 features, row polymorphism and functional dependencies. And we're using functional dependencies in a really crucial way here, right? To like infer types from other types. We can think of this as a type function on 2 rows that gives me back another row. Well, I can't write type class instances for rows because they'd all be orphans anyway, right? But what I can do is just define this class in the compiler and then have the compiler solve it automatically. And we do that for a handful of instances, right? So it's just this magic type class that like essentially lives inside is baked into the compiler.
Can
Can you explain how to read? Like, what's the comma mean there? The pipe?
Yeah, so pipe is all the functional dependencies occur to the right of the pipe. The functional dependencies are separated with commas. And every functional dependency is, says these inputs give these outputs, right? So if you know R1 and R2, you know R3. In addition, if you know R1 and R3, you know R2. Okay.
So is that a disjoint union then?
It is, no, you can have duplicates, right? So when you union, you might produce a row that has duplicates.
But if you know R1 and you know the result of the union,
Did I get it the wrong way around?
do you also know the thing that you unioned with?
I think we actually have all three. If you know any two, you know the third. I forget the details. That might be wrong, but I think we actually have all three. In the way the compiler implements it, I think you do actually have the property that if you know two, you know the third. So.
I don't know how you could implement, or I don't know how you could solve the R1 and R3 gives you R2, unless it were like a disjoint union, because then there could be like several different.
Well, the inputs don't have to be disjoint, right? But it's unions taking duplicates into account, right? So if I union foo has type A with foo has type B, then you get a row with foo twice, A then B. Right, so it really is just sort of subtraction, like just, it doesn't mean that I have to have a solution, right? Like it says if you have a solution, it has to be the only one.
Okay.
Yeah.
So R1 could be foo has type A, R2 could be foo has type A and bar has type B.
Yes.
And R3 would be then the same as R2.
No, it'd be
No?
foo, bar.
So there are two foo A's there.
Yes, exactly. So it's really crucial that when you define the meaning of a record, you make sure you pick, if you have duplicates, you pick the type that's consistent with this, right? Because when I union, I want to make sure, I pick the right one, and I might have duplicates. Anyway, I just wanted to quickly say, like, there's this idea that we can use functional dependencies and row polymorphism together to add these sort of magic type classes into the compiler, right? We can't write instances for rows, but we can we can automatically solve like a small set of constraints on rows inside the compiler, and that gives us like a small language for doing things that you might want to do on rows, like maps, zips, unions, intersections, and that's something that's sort of in the works at the moment. So it gives us this nice sort of like type language for working with rows. So.
The order of a row matters?
The order of the different labels with respect to each other can be reordered. Duplicates of the same label cannot be reordered.
When you reorder, are you just talking about you're looking for something? Why would you reorder? Just for optimization? If you unify two things, you can think about it as like I have to reorder one of them to get them in the right shape to unify them. If you think about them as lists. As a data structure, you can think of it as a map from labels to ordered lists of types, if that helps. I hadn't thought about like if you had a name in each one when they were different types. Like one was a string and one was whatever a name is. Then you can have two names in the merged row, but they're different types.
They can have different types, yeah.
Yeah.
We actually use that in, so with the extensible effect, it can be handy in a couple of places. I mean, the duplicate labels doesn't show up all that much, but I think having duplicates was probably the right choice.
Sounds complicated.
Yeah, we didn't used to have duplicates, and we used to actually have a check that at the end, part of the cleanup pass was to make sure nothing got unified that generated duplicate labels. But now we allow them. Okay, cool thing number 3 real quick. Polymorphic labels, right? So as a quick demo of like the unreasonable effectiveness of fundeps plus row polymorphism, another thing we can bake into the compiler is this row cons thing, right? Which if we could think of, a row as like a list, an association list, right? Then I should be able to con something onto the front of it. So if you give me a type level symbol L representing a label, and a type that's going to go in that label, and a row, then I'll give you a new row where I've consed L, A onto the front of it. Right? So if you know L and A in the row, then you know the output, so it's functional in the direction you want. But you can also extract the type if you know the label, right? So that means I can write polymorphic lenses, for example, for records, right? If you give me a value level proxy for a type level string, then I can give you a lens that lenses into that property inside your generic record.
Does everyone know what associationist is?
Oh,
That's what you're talking
just, well, I suppose I should just say this class adds on a new label and type to a type level row. Yeah, sorry.
Given that ordering for constraint for duplicate labels, do you actually need R1 in the second function dependency there?
In the second one, R1. So that says if I know the label and I know the row and I know the output after I consed it on.
Right. I think you only need to know the output because you've got the ordering of duplicate labels.
That's correct. Yes. In fact, I could move R1 onto the right-hand side there, I think. It's almost certainly true that the compiler's right and I wrote it down wrong here. Yeah. So this is really powerful, right? This lets me write one lens for every record property. You know, any record property I could think of. You give me this symbol, this type level string that I'm going to turn into a label. And you have to pass me like a symbol proxy for it, like to let me know the type. But then I can give you a lens that lenses into a record that gives me a type, the type that I wanted. And the thing that makes this type safe, right, is the fact that A has to be related to R2 by this row cons thing. It says that A appears at label L inside R2 because I consed it on. Okay, so it gives us this polymorphic label concept. And this is kind of a novel, I think it's kind of a novel approach to polymorphic labels. It just sort of fell out of the functional dependencies and row polymorphism stuff, which was really nice. Another example of this is, you know, if you want, so we can think of records as like, you know, anonymous products of different types with labels, right? Well, what if we wanted anonymous sums of different types, right? Data constructors in PureScript and Haskell are nominally typed, right? They're not anonymous. They have, you know, a data type declaration introduces a new name, but we have this thing called variance, polymorphic variance, that appears in languages like OCaml. And we can just emulate those. We can just build those as a library in PureScript using exactly the same stuff, right? So instead of lenses, if I just turn this, you know, if I change this into a prism, this is now a function that can be implemented, right? If you want a prism that looks at a certain constructor, and you can give me a value level proxy for a type level string that's the name of that constructor, then I can build you that prism. Right? And this is implemented in Nathan's PureScript variance library. So there's a lot of stuff you can do with this functional dependencies row polymorphism combination. I think it's really powerful, which is why, you know, functional dependencies is like one of my favorite feature additions we added. And then one other thing that I think is really cool that we have that Haskell didn't have until recently, but they just added it in 8.2 or whatever the very latest thing was, is this feature that we tacked onto type holes. So if you're familiar with type holes in Haskell, right? If you're halfway through writing a program and you can't remember what bit goes in, you know, where you are, you can just put a type hole and say, please figure this out for me. And Haskell will say, the type of the type hole is this thing, right? It'll gather all the constraints from the type checker that are relevant to the typed hole, and it'll figure out what the type of the typed hole is and tell you. And then you can use this for type-directed programming, right? So now you can just narrow down and sort of iteratively write your program piece by piece, refining type holes into smaller type holes. But what PureScript will do, which is really nice, I think, is that we'll also go through and use the subsumption judgment from the type checker to check all of the things that are in context for programs that are valid substitutions for the type hole. So if you do this in PureScript and you say, okay, I want this flatten function that takes a list of maybes and gives me a maybe of lists, and you just say, I forgot what the function is, it will say, it's sequence, right? Its type is more general than the one you thought of, but it's okay because the subsumption relation told us that it's, you know, it's a valid substitution for the typed hole, okay? So it's like a nice little addition to the type checker, I think, that like really helps I use this all the time. It's one of my favorite features in PureScript. Really helps a lot with type-driven development. And the implementation is really straightforward to describe. You just basically go all the way through all the terms in the context. You use the subsumption judgment to just check every type against the thing you had in the environment, and if it's a match, if the subsumption judgment doesn't throw an error, then it's a match and you report it. And then at the end, you just repeat the cleanup process, just to make sure that in the process of testing this thing, you didn't have like a column escape or something. And Christoph, who is one of the core contributors to PureScript, wrote about this in his thesis. And if you can get him to give you a copy of his thesis, then you can read about it there.
Is it not possible that there's an infinite number of types it would have to try?
No, because I only have so many things in context, right? I only try named functions that you have in libraries you've imported. So there's a finite number of those, unless you have like some, you can't have an infinite amount of code, right? So we just try each one of those, and we just run subsumption against each one.
Things with one that you wouldn't try, like after X and Y.
So crucially, what we don't do is we don't try and find every generalization of a type and test it for equality, right? That's what the subsumption judgment does. It says, is this type more general than this other one? But I don't have to sort of guess what the more, does that make sense? Sorry.
Kind of.
Yeah, so if I say, I want something of type int to int, the compiler can say the identity function has type for all a to a, which is not the type you asked for, but it's more general, so it's okay. And the subsumption judgment is the function that tells me for all a to a is more general than int to int. But I don't have to guess for all a to a or something, if that, in which case, yeah, you might run into that problem.
You did a good talk on that recently, all the things he wrote that can work in Atom and Vim and Emacs and all kinds of stuff.
Oh, Christoph did?
Yeah. And,
I think I missed that one.
So you can do all kinds of things, like put your cursor on a thing and it changes the whole, and it was almost looking like Idris.
Yeah, it's
write code for you.
It's really cool. He had a nice example where it was sort of like very real world, where you have different entities in a database and keys for each of those entities, and you have like a polymorphic fetch function, for example, that gives a key and gives me the entity type for that key. And then a handful of sort of helper functions to go with that, and then you just have type holes, like try and write a program that would like fetch this, loop over this list, fetch each one of those, and then it would always infer the right, even though everything was way more polymorphic than you needed, it would always infer exactly the right fetch function, which I thought was really cool. Okay, super quickly. Future work. I would really like to have instance chains. It's been on the to-do list for a long time. So the problem, you asked about overlapping before, right? The problem is sometimes you want to write type functions like this. If I want to determine whether two types are equal or not. Did I write this wrong? This is wrong, I'm sorry. So this should say, have some result, where the result is a type level Boolean, right? So those things are equal and these things are not equal. Okay. The problem is that these are overlapping.
Let's go first read through what this says.
I want a function that given two types tells me if they're equal or not. Right. So it's a function from two types to a type level Boolean R, true or false. Okay. If you give me A and A for any A, then they're equal, so it's true. If you give me A and B, they're not equal, so it's false. The problem is I have to try this instance before I try this instance, because this instance applies to everything. They're overlapping, okay? And they're overlapping. You might say, oh, true and false are not, they don't unify, but the problem is there's a functional dependency, right? So I only have to know A and B in order to choose that instance. So what instance chains do is let you put an ordering on, they let you make a chain out of your instances and say, try this one, then try this one, etc. So there's a lot of different ways, and actually there was a really nice post yesterday, I think, on Reddit Haskell, a proposal for apartness constraints, which is sort of an alternative to this, and there's a whole bunch of different alternatives, but we try and decide what the best one is, and we'll go and implement something like this. And I think this will be one of the last pieces in like the type level programming.
Is this like lifting pattern matching to a type level?
Yeah, you can think of it that way. So with like the type level prologue stuff, you know, you have these goals, but they can overlap, right? This is a way of like making it really like pattern matching. So like try this, then this one.
So do you see that would eliminate the need for like closed type families entirely, and just eliminate the need for type families?
So I don't know if there's cases where you need type families that functional dependencies wouldn't do the job. Certainly the way I use functional dependencies and type families, I haven't run into any. I don't have any plans to implement type families, closed or open, because it would require some really serious changes to the type checker, I think, and functional dependencies is like I say, a lot of benefit for such a little implementation right now. So yeah, in theory, I'm not sure. In practice, yeah. And then the other one is constraint kinds, right? So just like we said with higher kinded types that we could abstract over type constructors, well, constraint kinds lets me abstract over constraint constructors, right? So if I want to write a map function on rows, but where I'm allowed to, you know, so this says, you know, you give me a function, I give you an input row and an output row and a function that maps types to types, right, via a constraint. Then I can sort of map that function over the rows, right? If I want to implement this, then I need, or if I want to implement it generically, I need constraint kinds, right? Because I need to be able to say, I need to be able to parameterize all the constraint constructor that represents my function. Okay. So these are the two last pieces in like the puzzle for like type level programming with rows that I'd really like to have in PureScript. I have some references if people are interested. My favorite paper for like Haskell 98 inference is Typing Haskell in Haskell by Mark Jones, which is sort of like very easy read, like functional Perl type of paper. Very much recommend it. If you're interested in higher rank polymorphism, there's a paper called Complete and Easy Bidirectional Type Checking for Higher Rank Polymorphism, which is excellent. I took a lot of cues from that, and the HMF paper is also great, but it's not quite as close to what I talked about, although it does talk about columnization. Type classes and fun depths. The original type class papers are great. How to make ad hoc polymorphism less ad hoc by Phil Wadler is a great paper, and the original functional dependencies papers by Mark Jones are also great. And Mark Jones also co-authored the instance chains paper, which has a nice summary of some of the fun depths material as well. If you're interested in extensible records, Brian McKenna has a fantastic blog post from a few years ago called Raw Polymorphism Isn't Subtyping, and he also implemented the ROY compiler, which is where I originally saw raw polymorphism and wanted to implement it. And then Dan Laarhoven, I think is how you pronounce his name? Not sure, but from Microsoft Research has a bunch of interesting papers on extensible records with other interesting things like scope labels, first class labels, and he also wrote the Coca programming language, which also has row polymorphic effect types, just like PureScript, but with different elaboration. And the Ermine compiler is also a great resource for row polymorphism. So that's it. Yeah, questions?
Is the reason PureScript is strict purely an artifact of JavaScript being strict, or were there other considerations like simplicity?
So I came from TypeScript, and I wanted to have the same property that I had with TypeScript, where I could completely predict what the compiled output would be like, so that when I went to debug it, I would just know, like, be able to read it immediately. It's obviously much more difficult to do that in a lazy language because, well, you need a runtime to implement laziness, and everything has to go through the runtime, right? So that was the original reason for strictness, and obviously it comes with a lot of trade-offs. I use Haskell every day, and I love laziness as a general, as a default, but it's a really interesting challenge to sort of implement some of the things you would do in Haskell in PureScript, and you always have to have strictness in the back of your mind,
Are there any transpiler attempts that go from lazy to JavaScript?
There is a Haskell backend for PureScript. So one thing PureScript has is the ability to switch out the backend. We can stop the compiler after generating the intermediate representation, which we call functional core, and you can output it to JSON, and people have written backends for like Python and C++, 11, Erlang, and so one backend actually targets Haskell, which is an interesting choice because obviously Haskell's lazy, and it uses a Haskell library to implement row polymorphism. So there's sort of an interesting question. It's like if you take a language which is designed for strictness and all this, standard libraries are strict, implemented with strictness in mind, to what extent can you just compile that to a lazy language and like sort of hope for the best, right? I don't know the answer, but it's possible. Yeah. Any other questions?
From an anecdotal level, how much does the PureScript community miss laziness, if at all?
So there are some really interesting challenges that come with choosing strictness as the default. So one library that I wrote recently was like a little FRP library, and it took me the longest time to figure out how to do FRP in a strict language. You can't rely on sort of, Haskell, with Haskell you have this sort of wealth of knowledge that's, built up, but a lot of it depends on using, laziness, like crucially, right? And so you can't just take it and just naively translate it. Yeah, even simple things like monad transformers, right, or like free monads or things like this are not, you can't just translate them over. So it sort of presents some interesting challenges, but it has its own benefits as well. So yeah.
Strict folder is the worst.
Strict folder, yeah. Yeah.
It's kind of like how in Haskell you want a strict folder and a lazy folder, and it's kind of like the sweet spot. And in PureScript we have a strict folder, which just makes foldable kind of useful.
Yeah, if you want lazy lists with like lazy folds and lazy right folds and a library of lazy right folds built up, there is a library that provides that. But it took a little while to get it right because we couldn't just port it naively from Haskell. But you can build. So the answer is you can build all these things using laziness as a library. It just takes some sort of cunning and a bit of it's just difficult in some cases. Yeah. Yeah.
Are you gonna have the category theory group at all, or?
Category theory group? Yeah, I was gonna mention that later actually. I'd love to get that started. Yeah. Should have brought that up in the announcements actually. Yeah. So there's some talk about having a category theory study group if anybody's interested.
I'm interested.
Yeah.
Cool. I have a feeling it's going to be really advanced really soon.
I was thinking we could like go through one of the sort of like introductory texts, like products, limits, equalizers, all the sort of basic bits and pieces first of all. Yeah, questions?
Is there any plans to target WebAssembly?
Not directly, but the C++ 11 backend can successful go via NScript into WebAssembly.
No.
So, you don't want to transpile twice, right? But you can do it. Yeah. It would be nice to have a WebAssembly backend eventually if they figure out the GC thing. I don't particularly want to write a garbage collector though, my focus is mostly on like the JavaScript backend at the moment. I just want to make it possible for other people to write other backends, yeah.
What are the big things that you wish PureScript had that Haskell has?
GADTs, type families, I want them, but I don't want to implement them. So, yeah. What else? Sometimes laziness I would really like to have something like, I don't know how this plays out in a practical language, but there's this idea that you can have evaluation order polymorphism, right, where I can write a program once that can simultaneously be lazy and strict, and I can sort of choose at the call site, or I can defer the choice. I think that would be nice to experiment with, but it sort of doesn't play nicely with the no runtime requirement. You can do something a little bit like that with libraries, but it gets a bit messy. Yeah, mostly GADTs type families. Did you have a question?
I was going to ask, how close is the PureScript compiler to JRC? I know it's missing it's missing features, but is it modeled at all on JRC?
The implementation?
Implementation and organization?
No. So, I mean, I've read like the typing Haskell in Haskell papers, and I've read a lot of the papers that, describe the implementation, but I haven't read the GHC implementation specifically. It would be interesting. Yeah, I would like to get familiar with it, even if just to make some contributions at some point. But no, it's not directly based on it.
Just generally, so when you started, what part of the compiler did you start writing first? Was it the
Sure.
checker?
So I had bits and pieces, right? So like, every Haskeller eventually learns about parsec and things, right? I had to write parsers. I read the typing Haskell in Haskell paper, so I had bits and pieces of a type checker lying around. Code generation, is string concatenation for all intents and purposes, right? So, I had the basic pieces, and then when I started, I just took what I had and glued them together into the first prototype. The interesting bit that I didn't have was row polymorphism. We had that sort of from the get-go. So most of the work initially was done on the type checker. That was the piece I needed to do most on. Any more questions? No?
Yeah, how similar are the cores?
Are the what, sorry?
The functional cores.
So functional core is basically a little lambda calculus with records.
How similar to Haskell's?
So the functional core, I don't really know enough about GHC core to say. They're both, essentially lambda calculi. I think the GHC core has constraints now, like system FC, right? You got to have constraint coercions, in the functional core. Obviously, we don't have that. But in the sense that they're both basically lambda calculus, they're quite similar, I suppose.
I know GHC is typed as PureScript.
No, it's not. Yeah. I would like it to be typed. The problem is with the elaboration semantics that we have in the type checker for type classes, I'm not exactly sure how to keep it typed and still be able to have that. And also how you deal with scolums in the elaborate, because scolums then appear in the elaborated functional core, right? So I'm sure it could be worked out. I just never really thought about it too much. But
There's a paper called trees.code.
Hey.
That might help with that.
Oh yeah, so you like attach stuff with functional type families or something. Right? Yeah. So that's something we really would like to have. So having annotations of different types that appear on the different, in the types and terms and things that can change during the different compilation phases would be really great, because what we have right now is basically like it's all one annotation type, and we use like maybes or something to make sure. So it's not ideal. The reason I did it that way was that I didn't have a good solution at the time that wouldn't be really that wouldn't use some like really advanced Haskell, and I didn't want I don't mind sort of like bits and pieces of the compiler depending on advanced Haskell, but I really don't want like the ADT, like the basic core of the compiler, to have like advanced Haskell in it, because I want people to contribute to it, right? So but it's getting to the point where it's getting a little bit silly now. We're like passing around this like huge annotation type that has all the stuff we need. So it might be time to look at a paper like that.
At what point do the other backends plug in? Do they
Right.
get access to the type information?
So
or do they just get the functional core?
they don't get the type information right now. So the C++11 backend. Right. So So the C++11 backend actually is a fork of the compiler, right? So it was started before we added the ability to dump the functional core. So it's still just a fork of the compiler, and it's probably not possible to have it work on the functional core. The functional core approach is pretty new. Like most people haven't used it yet. The Erlang backend, I think, is also a fork. So, yeah. Any more?
Will I ask my own question?
I don't know if I'll be able to answer it, but sure.
This is like a random neurons firing kind of stream of thought question, but the duplicate fields and records, I feel like I read a little about that in Evan's thesis. Is he
Not
related
sure.
to that anyway, or do you know?
I don't know. I seem to remember at one point reading that he used the extensible records with scope labels paper. So it maybe, I'm not sure.
Elm now is based on PureScript, and then it maps directly to JavaScript object, but you don't have.
Oh, that's right. Yeah, they changed that. Sorry, go ahead.
So it's not scope labels anymore. They took out the addition, the field addition and deletion from the language. So it's just like PureScript.
Okay.
But do they have duplicates? Do you know? I don't know if they do. They actually are like objects, aren't they?
Because it's only used to model records. Like you can't use rows or anything else.
Oh, I see. Yeah, good point. Okay.
Do you have an opinion on something?
Yeah, I think it's a great language. Like, it's you know, a great way to learn. Well, sorry.
I just thought it was similar to PureScript.
Yeah, I think it used to be the case that Elm was UI focused, you know, and PureScript was building little DSLs focused, and now, you know, PureScript has a lot of libraries for building UIs, and Elm has become a more general purpose language, right? Now not everything is based on FRP anymore even. So, you know, the differences are more subtle now, right? PureScript, you know, I think it obviously has the more advanced type system features. Yeah, I mean, I think Elm is a fantastic language for like learning, you know, functional programming concepts in a pure functional language coming from JavaScript, right? And we tend to find that eventually some of those users want some of the, you know, if they've used Haskell or whatever, they want to use those type system features in a language like Elm, and then they find PureScript and, you know, they continue that way. And other users tend to just stick with Elm and it meets all their needs. So I like the fact that there's both. Yeah.
Is PureScript in PureScript still a goal?
No, it's been sort of sat a bit rotting for years at this point. I would eventually really like to try the C++ backend as an alternative, because the problem wasn't that we couldn't implement it, it was just that it was horribly slow. And it wasn't necessarily that PureScript generated very slow code, it was because we also tried it with JC.js and they were like pretty much exactly the same speed. It's just that JavaScript isn't really a great runtime for compilers, you know? That's my opinion anyway. So yeah, I'd really like to try it with the C++ backend at some point and try to see if we can match the Haskell performance. And I don't think, I mean, Haskell's optimizer is amazing, right? So that's going to be a tough job, but it'd be an interesting goal to have, but it's not the focus at the moment. Yeah.
So you're saying that you want to try and write the compiler in C++?
No, write the compiler in PureScript and use the C++ backend to convert it to a native executable. Yeah.
Is there any sense of the performance difference between just somebody who really knows JavaScript and somebody who writes something sort of equivalent in PureScript? Is it basically the same speed, same memory usage?
So naive, you know, writing PureScript naively, because everything's, you know, the runtime, every function is curried, right, can result in some fairly, you know, unoptimized JavaScript, but it's not the end of the world, because usually, you know, a few function binds are not the bottleneck, right, when we're writing web applications. If you need something that's really optimized, like, so a good example is probably the virtual DOM thing, right, you had. There are tricks, and it's, you know, there's some pretty hacky tricks you can use to get fast JavaScript out of the PureScript compiler, if you really need very fast, and like, to the point where the virtual DOM, Nathan, you should probably just say, like, the...
No, it's kind of I've kind of developed an art for coercing the compiler to give me the JavaScript that I want. So there's like all these, like, you know, it makes, for the most part, it's, you know, it's okay, it's kind of what you'd expect, but then like all the optimizations are pretty much opt-in. So it's like if you want to create functions, well then you can use this, you know, this special data type, function data type that's not like the normal function data type, and call it, and it'll inline all the calls, so you don't have that overhead. And like the inlining for F kind of removes all the binds and stuff, so it just looks like imperative JavaScript. So if you just stick to that kind of like very specific kind of like effectful code, you know, it can be pretty fast. But it can still kind of, because effects are values, and so anytime you want to run an effect, it also generates a closure for that effect, so that it can run it multiple times if you needed to, because it's a value. That creates a lot of extra allocations in hot code. And so there's probably some other things there's an optimization we want to do for what are called FFNs. So like the optimized function type is FN, just called FN, and it'll inline those call sites, and we can do the same optimization for effects, and it can inline the actual effect at that point instead of creating another heap closure. And so that's the biggest bottleneck. I wrote a virtual DOM library for it for our UI framework. And that was, the garbage was the biggest issue, as far as really hot code. And effects were a big part of that. So you had to kind of have to navigate that. You can be really, really fast code. You have to navigate that. But I think for the most part, it's not a big deal. It's a lot faster than you think. And I think writing idiom, it's funny because I've done a lot of performance testing too, and writing idiomatic PureScript code runs a lot better in Firefox. Firefox, for whatever reason, is really good at optimizing the kind of code that we generate, versus Chrome is really good at optimizing code that a JavaScript person would write. And so it's when I write the kind of when I'm trying to coerce the compiler to write the optimized code, Chrome optimizes that a lot better. But if you just write idiomatic code, Firefox optimizes it a lot better. I don't know.
Can you mind functions be compiler? Check that.
Yeah, and there is, so there's a rollup plugin. Rollup's just a bundler. And there's a rollup plugin out there that will do that for you. It'll generate inline versions of function, or uncurried versions of function. And when you go to bundle the PureScript output, it'll parse the PureScript output and insert uncurried versions of functions. But last time I tried to use it, there was a parser issue. The JavaScript parser we were using, it wouldn't parse some of our output to, I don't know, it was kind of weird. But we haven't used it at scale yet, so I don't know how well it works or what the speed difference is like.
I guess you can't really do it if you have a library or something. Other things, right?
No, because you can because it's a single pass bundler at that stage. You've already compiled it, you have all of your blobs, and so it's bundling your entire program. And since you're able to bundle the entire program, it can do the whole program analysis.
Okay.
All right, thanks.
All good. Equal to false, and everything else is not equal to everything else. Okay, and one basic but really useful feature of type classes is that you can use type classes to you can build type class instances out of old type class instances, right? So if I want eq for lists, well, I can give you a sensible definition of equality for any list type, as long as the elements themselves have a sensible definition of equality. Okay, so I can say that I have an instance called eq list for eq of list A whenever, and that's what this arrow here means, whenever I have an instance for eq on A. Okay. Any questions on that first of all?
Just wonder, we all just got a meetup thing that someone's trapped downstairs.
Okay. Okay, so just going to fly through some of these ideas from Haskell, right? So another one that we borrow from Haskell that a lot of languages don't have is higher kinded types, right? So in PureScript and languages like PureScript, you can write these data type declarations, right? Where you have a data type and then a bunch of type arguments, and then you can use them to build your data type out of those type arguments, right? But crucially, in PureScript and Haskell and a few other languages, the arguments don't have to actually be types, right? They don't have to represent types. They could represent type constructors, so they could be functions that take types to other types, as an example, right? So this is an example where A here is a type, right? So for example, I can construct this free thing with this pure constructor by just giving you a value of type A. But F isn't a value, right? F isn't a regular type, like a type of values. F is a representation of a type constructor. It takes types and gives me new types back. Okay, so I can apply F to a type and get a new type. So for example, I could apply free to list, which is not a type itself, but it's a list of A as a type. Okay, list is a type constructor. Okay, so when we have the ability to talk abstractly about type constructors or type constructor constructors and what have you, then we say we have higher kinded types, okay? Because we can classify the different sorts of type constructors using this notion called kinds.
So how do you know, looking at the signature, that in free FA, F is a constructor?
Right, so what's happening here is we have essentially type inference going on one level up at the type level, inferring kinds, right? So just like types track the types of values, just like types characterize values, int is different from string, kinds characterize types and type constructors, okay? So the kind of a list is a different thing from the kind of integers, for example, right? One is a type constructor, so we classify them with kinds. And we can do kind inference just like we can do type inference. So what happens here is when I type this declaration in, kind inference works out, even though I didn't write this as a type constructor, the compiler can figure out, well, you applied it to a type and you gave me back something that was in a type position, so it has to be a type constructor. Okay.
What happens if there are multiple kinds for which?
Hi, if we haven't met, I'm Phil. I created the original PureScript compiler, and I continue to work on it. I'm going to give an overview of the PureScript type system specifically. So just the type system, PureScript, the entirety of PureScript is kind of a big topic to present in like an hour, I suppose. So I'm just going to focus on the type system. I'm going to talk about some stuff that we nabbed from Haskell that you are probably familiar with if you've used Haskell, and some stuff that we have that Haskell doesn't have as well. Okay, so I'm not going to give sort of an introductory sort of talk on PureScript. If you know Haskell a little bit, you'll sort of see what's going on with the few bits of code that I have. But the very, very high level quick summary is that PureScript is a small, strongly typed programming language that compiles to JavaScript. It's heavily inspired by Haskell, it's written in Haskell, and it's specifically designed to target the web and front-end development specifically. So you can learn more at purescript.org or on the PureScript channel on either Slack, the FP Slack, organization, which is probably the best place, and then there's a PureScript IRC channel on Freenode as well. So the goals I had, I should just say, by the way, stop me if you have questions. I don't have that many slides, so yep.
As an introductory comment, can you say a quick word about contrast with YESID, ups or downs? Well, I can talk about pardon me, contrast with like Haskell specifically, like Haskell generally, as a language, and then I'll talk, I guess, a little bit about YESID. But so the major difference between Haskell and PureScript is that PureScript is strict, Haskell is non-strict. Okay, so that has a lot of repercussions in terms of the way you write code. If you write in if you're writing in a strict functional language, a lot of the idioms don't directly translate over, but there's still a lot of things you can take from Haskell and bring over to PureScript and be productive. There's a few other differences. Mostly, I can summarize it as saying, PureScript was built specifically with the web in mind, right? So, it's a strict language. It compiles to really sort of readable JavaScript on purpose. Those are the main things, but I'm going to talk specifically about some of the differences in the type system in a little bit anyway. Comparing to YESID, if you're not familiar, YESID is a web framework for Haskell. You would write a more traditional sort of back-end driven, web application using YESID. PureScript tends to focus more on the front end. You can write back-end applications in PureScript, but you'd be more likely to write like a single-page application in PureScript than do something like you would with YESID. Okay. Does that answer your question? Yeah. Okay. Cool. So yeah, please interrupt with questions because I don't have that much material to get through. Yeah. So just quickly a little bit about the goals that I had in mind with PureScript.
It would be for which it would work out.
Right. So there's some extensions in Haskell like polymorphic kinds, right? The polykines extension, which lets you do similar sorts of kind inference, for types that you would want to do for polymorphic values. So like we can have polymorphic types
or parameterize over polymorphic types and all these things. Maybe we want to do the same things at the kind level. PureScript doesn't have polykinds, but you can do some of that stuff in Haskell. I'd like to add polykinds eventually, but we don't have it right now.
So if you don't specify what kind it is, and there are multiple kinds that will work, does it just assume its kind is type?
It just defaults to star, yeah, type,
Okay.
yeah, exactly. I've tried a couple of times to get polykinds to work, but it's a little bit tough to get the details worked out. But yeah, it's on the list. So, okay, and just like, well, why do we care about this, right? Like, why this is not just like, this is actually useful, right? So the reason is we can parameterize things like classes or functions, or the types of functions, also over higher kinded types, right? So I can write a map function for arrays, or I can write one for lists or binary trees, parameterized over the types of the values in its leaves, right? They're all similar sort of concepts, and they obey the same laws, right? So why should I not be able to write one function that does, that implements all of those mapping operations, right? And I can, because PureScript allows my type class definitions to refer to higher kinded types, right? So I can say functor f, the type constructor f is a functor if whenever you can give me a function from a to b, I'll give you a function back from containers f full of a's to containers f full of b's. Okay, so I can implement this for lists, arrays, and whatnot, but I can use it generically. Any questions? So it just enables a new type of code reuse. Any questions on that?
Is that an extension necessary in Haskell?
No, that's that just comes with Haskell 98. Yeah. Okay, so the next feature we have from Haskell is functional dependencies, right? And this is one of my favorite features in PureScript because it has such like a high power to weight ratio, right? Like we didn't have to do all that much work to add it, but it enables so many things, and I'll talk a little bit about some of the things it enables. So if type classes are like predicates on types, right? Then if I allow myself multiple types,
I gotta parse that. Type classes are like predicates. Okay.
So we said like the eq type class is like a predicate, right? Like a type may or may not have decidable equality. Well, the generalization of a predicate on a type is a relation on multiple types. So if I allow myself multiple type arguments here, then I can talk about relations between types and between type constructors and things like this, okay? So for example, in the MTL library in Haskell, there's this type class called monad state, which allows you to talk polymorphically, generically about monad transformer stacks that support the state operations, okay? If I want a monad that allows me to get and set a piece of mutable state, that might be the state monad, or it might be the state monad transformer transforming some other monad, right? There's lots of different monads that implement that interface. And in general, we have this class to talk about them abstractly. And it's a relation between two types. Well, a type and a type constructor. Okay, so S here is the type of the state I care about mutating. And M is the monad that I'm trying to state. This monad contains this ability, right? Has the ability to modify the state. Now it turns out when you have relations between types and type constructors, it's often useful to be able to say things like, compiler, if you can infer this type, then you can also infer the other type, right? If you're trying to solve this, if you're trying to find an instance for this and you only know about M, then this functional dependency says that you can figure out S, right? If you choose an instance for M, then you can just take S to be whatever that instance said it should be, okay? You don't have to match M and S both. You could just match M and infer S, okay? So this is really powerful because it allows me to talk polymorphically about monads M and then not worry about like having to put type annotations on the state type, because if I didn't have this functional dependency, in some cases the compiler wouldn't be able to figure out which instance in some cases. So functional dependency is like a really practical thing when you want to do things like use the monad transformer library, but they also enable a whole bunch of other really interesting things. Yep.
So if you're writing, it's only when you're doing inference that that's the case, right? If you were writing out the, because the S comes before the M, so you couldn't like just give it M without giving it?
Yeah, so the order here doesn't matter.
Okay.
The order on the right and the arrow, right, the direction of the arrow matters. Okay. So this says M determines S.
That's for writing this type class instance, right? But if you were going to write an implementer, you'd actually have a particular S in mind. Is that what you're getting at?
I guess so.
I don't know.
Yeah, I should have probably written a little bit of code to illustrate this, but it's sort of tricky to see exactly why the compiler needs this information. But in some cases, you'll end up where you think it's so obvious that like it should have picked the monad state instance for like this particular monad, but it didn't because it couldn't, like, if we didn't have the functional dependency, the state type wouldn't have matched because I was using it like polymorphically or something. Yeah, in practice, it's just really handy to be able to talk about these relations this way.
Does this state that when you create an instance of monad state that you have to bake the S into that instance or not?
Yeah, so typically you'd say something like, so as an example, M might be the state monad, right? State S. In that case, I'd write something like instance monad state of S for state S, right? And the compiler might know that it's state. I'm using state of something, in which case it can infer the S must be whatever was inside state. It has to be the same one. Okay, so this is just useful for sort of, in practical terms for using things like the MTL. I wanted to build a language that I wanted to use every day. At the time I wrote it, I was using TypeScript and JavaScript. There were a lot of alternatives for writing strongly typed compile to JavaScript languages, like Roy was probably one of the ones that I took the most influence from. What else? So now there's things like Flow. There was Elm at the time that was just getting started, JC.js, Haste. None of them really did exactly what I wanted, so I tried to sort of piece together, the rudiments of exactly the language I wanted, and then we got a lot of contributors, and now it's obviously a much bigger language. To explore how types can improve web programming was one of the goals, to try out just some new type system ideas. One of the stated goals of GHC is that it should be sort of a playground for new type system ideas, that researchers should be able to take their new idea for a lazy compiled strongly typed functional language and just add it to GHC and see how it works. So I wanted a similar sort of thing for PureScript, where you could just if you knew how to build a Haskell project, you could just sort of try something out and make progress with ideas really quickly. And as well, just have a fun project for people who are new to open source Haskell. So if you're interested in joining the PureScript community, there's a lot of sort of small tasks that, interesting small tasks that can, to be done on the compiler. If you want to contribute to an open source, like a major open source Haskell project, there's a whole bunch we can help you get started with. Basically, just have to know how to build a project with Stack, and you can get started. Okay, so quick agenda. I'm going to recap some Haskell extensions that some of them are pretty common, some you might not have seen in a while, so we'll just go over them. Talk about the implementation of the type system a little bit, and those features, how they get implemented just at a high level in the PureScript compiler. I'll give a couple of quick demos of some features that we have in PureScript that we don't have in Haskell. And then I'll just talk a little bit about some ideas for type system features that we would like to add, ideally before like a 1.0 release. Okay, so a few Haskell extensions, or just features I suppose to begin with. So hopefully everyone's seen type classes before. A lot of the features I'm going to talk about sort of build on type classes pretty extensively, but the basic idea is that we want to capture like predicates on types, right? So if I want to talk about types that types A that have decidable equality, right? I can test equality of two values of type A. Then I can build a type class called eq for equality to do that, right? And so I have a class called eq. It has one type parameter A, and it's built out of a method called eq with a lowercase e. That takes two values of type A and returns a boolean that tells me if they're equal or not. Okay. And instances attach basically assert that a type is a predicate holds for a certain type. Okay. So this instance called eq boolean inhabits the eq type class for the boolean type, just true and false. Okay. And it's implemented using pattern matching. True is equal to true, false is